The next topic we are going to look at is the solution of nonlinear algebraic equation systems. We will first start by looking at one nonlinear equation in one unknown. Then we will extend the idea to multiple nonlinear equations in multiple unknowns. That means n nonlinear equations in n unknowns. We are going to look at several techniques for solving a single nonlinear equation or multiple nonlinear equations. But only the Newton method and its variants are scalable for multidimensional systems. Methods such as bisection method, regular-Falsy method, secant method, etc. work very well for one equation in one unknown, but they are not easily scalable for higher dimensional systems. So we will look at all these methods in turn. Something like the bisection method we have already looked at, but here in this video I want to take a look at the Taylor series expansion of functions and show you how it can be useful in solving one nonlinear equation in one unknown. So consider the system that you see here, a simple algebraic system where the variable is x and the function is f of x. So x is the variable, f of x is the function involving x. And the relationship between x and f of x is like what is shown in the red curve that you see there. I have marked 2 points on the red curve. One point at x is equal to x naught, where the function has a value f of x naught. Another point is at a distance of delta x to the right of x naught. So the next point that we mark on that red curve is at x is equal to x naught plus delta x, and the value of the function at that point is given by f of x naught plus delta x. So these are the 2 points. Now assume we are at the point x is equal to x naught where the function value is f of x naught. We want to find out the value of the function at x is equal to x naught plus delta x. So if you want to write an approximate value for the value of the function f at x is equal to x naught plus delta x, we might write this expression that you see there. The value of the function at x naught plus delta x is approximately equal to the value of the function at x naught, and then you add h to it, right? H is the vertical height between the points that you see there, okay? Between the red point, this value, and the black circle point, which has got this value of f of x. So that height is h. So we are looking at the approximate value of the function at x naught plus delta x. So this is approximately equal to, and we use f of x naught as the base, and we say we are going to increase that value by an amount h to reach the approximate value. If you want to reach the accurate value, you should increase it by h dash. Okay, but we are interested in a very crude approximation. Therefore, we say to f of x naught, we are going to add the value h to get an approximate value for function at x naught plus delta x. So this equation should make sense to us. So what is h now? H can be written as slope at x naught, slope of the function at x naught multiplied by delta x, because height by the horizontal distance is equal to slope, right? So this is the idea. The height divided by the horizontal distance is called the slope. So if you look at the slope of the function, that means the slope of this line that I've drawn as dashed line at x naught, that function has a certain slope which we indicate by the symbol f dash at x naught. That means it is basically df by dx at x is equal to x naught. That is the slope, right? Take the derivative of the function and evaluate the derivative at x is equal to x naught to get the slope of the function at x naught, which is denoted by the symbol f dash of x naught. Therefore, I can write the approximate expression for f at x naught plus delta x to be f of x naught plus, now h is replaced by f dash of x naught times delta x, using this idea that h is equal to slope times delta x, and slope is nothing but f dash of x naught. So f dash of x naught multiplied by delta x will give us h. So this is an approximate expression for the value of the function at x naught plus delta x. Now This will become more and more accurate. This will tend towards equality sign if we take delta x to be infinitesimally small. That means if you're not wandering too much from x naught, if you're wandering by very little, then this will become from approximately equal, it will become more and more exactly equal. All right. So for small delta x, this becomes more like equal to. For significant delta x, we have to put this approximately equal to sign. So this is the central idea to what we are going to do later. Let us keep this approximation in mind. We like this approximation because it is linear approximation and we are comfortable working with linear systems. All right. If we can avoid nonlinear systems, we would rather do that. So this linear approximation is very useful in many circumstances. Now, how do you get the exact value of the function at x naught plus delta x? That means we have to add to f of x naught, we have to add h dash, which is this height, rather than this height h, which is only approximate. So how do you get a good value of h dash? We do that by including other terms, right? So this you see is f of x naught. This is something we have seen earlier. This is h. Now we have to add other terms that bring in more information about the function around this point x naught. That means we would be interested in the curvature of the function. All right, this function f of x is a curve. It's not a line. So the linear approximation, right, assumes that the curve is more of a line around x naught. So for a small region around x naught, that may be true. But if you go a little wider, there is a curvature, right? And the curvature may be light or it can be severe. So if it is a light curvature, then maybe adding this quadratic term in the Taylor series expansion is enough. But if the curvature is strong and significant, we may have to include cubic terms, fourth power terms, fifth power terms, etc., onto the right hand side. So these terms, right, from the second order term to the third order term to the fourth order term, all the way till this infinite series, all the way down, those are called higher order terms. And they are not as significant in most cases because we are usually working with small delta x. So for small delta x, right, for example, if delta x is equal to 0.1, delta x squared is going to be 0.01. Delta x cube is going to be 0.001, etc. So these terms, right, are going to get smaller and smaller as we go to the right, and therefore it is not going to contribute much to the function as you go along. All right. So if you group all these higher order terms together, HOT stands for higher order terms. If you group all these things together, you can say there are terms in this expansion that is of the order of, so this is means it is of the order of, O means order of delta x squared, because we are going to truncate here because we are often interested in linear approximation of the function. So we are going to truncate it here and retain only this part. So what are we going to leave behind? What are we going to truncate? The part that we are going to truncate, the leading term has this delta x squared. And because delta x squared is going to be larger than delta x cubed, which is going to be larger than delta x to the power of 4, the higher order terms, when we drop them, the truncation error is dominated by the first term, which is of the order of delta x squared. So that is what the meaning of this is. So the accurate value of the function you can get if you include this infinite series rather than just stopping with the linear term as we did here. That's why we get an approximation. All right. So if you include the first second derivative information multiplied by delta x squared and divided by 2 factorial, and then you add the third derivative evaluated at x is equal to x naught divided by 3 factorial multiplied by delta x to the power of 3, etc., you will get more and more accurate value for the function at x naught plus delta x, even though delta x may be significant. So basically what you see here is called the Taylor series expansion, this infinite series. It's the expansion of the function around x is equal to x naught. All right. And if the expansion is about x naught is equal to 0, then it is called a Maclaurin series and so on, right? There are many series that we will see in calculus, but the most useful is the Taylor series expansion, TSE, Taylor series expansion. So that is this form. And then we are going to stop at the linear term because we are not interested in solving the nonlinear problem in all its glory in one shot, because oftentimes that cannot be done. So we are going to convert the nonlinear problem to its linear approximation, and we are going to solve the problem through multiple iterations, right? Multiple times we do the linear approximation, solve a linear problem at every time, and hopefully get to the solution of the nonlinear problem. So the exact value of the function at x is equal to x naught plus delta x is f of x naught plus the first derivative times delta x plus higher order terms. But we are going to be happy with this approximation. So with this background, let us move a little bit forward. So let's say we are interested in solving this equation. The general form of the equation is f of x is equal to 0. And to take a very specific example, we will take this particular problem where f of x is x squared plus 3e to the power of minus x minus 4.2, because the right hand side should be 0, right? So we bring the 4.2 to this side, which will become minus 4.2. So f of x is x squared plus 3e to the power of minus x minus 4.2. So what I'm going to do here is I'm going to try as a guess for the solution, right? I do not know what the value of x is, such that this will be f of x will be 0. I do not know what x is. So let's say I'm going to try an initial guess, say x naught is equal to 1. So I'll evaluate the function at x is equal to x naught. That means that x is equal to 1 in this case, because I've chosen x is equal to 1 to be my initial guess. The 0 indicates it's the initial guess, right? The guess at iteration 0, if you like, or the value of x at iteration 0. So I'm going to try this value of x and try to see whether magically or by great luck I get the right hand side to be 0. So if f at x naught turns to be 0, at my initial guess turns to be 0, then lucky, right? So we have solved the problem, and we can say the root is x is equal to x naught. So we have found at least one root to the problem. Okay, then if you are asked to find out all the roots to the problem, because a nonlinear problem can have multiple roots, then we can use other techniques to find the other roots. But let's say here we are just interested in finding one root. By chance, if our initial guess happens to make the function 0 at that point, then we have found the answer, and then we have got the root. So we can declare the answer. But oftentimes, right, f of x naught, the value of the function at x is equal to x naught, our guess, will not turn out to be 0. What if it doesn't turn out to be 0, which is going to be more often the case? So we need to improve our estimate of x, or we need to get a better value. So what I'm going to do is I'm going to say, well, I'm going to get a new value of x by taking my previous value of x and adding a correction delta x to it. Okay, I'm going to add a correction term delta x to my previous value of x, and then I'm going to take the new value of x and I'm going to try out the same thing. I'm going to see whether at this new value of x does the function become 0. If it becomes 0, happy. If it doesn't become 0, I again correct my guess, right? So it is basically smart trial and error, okay? That is guided by an algorithm. In this case, this is called the Newton algorithm. Okay, so now what is the value of the function at the new point? The value of the function at the new point is f of x. And that can be written as f of x naught plus delta x. And we just learned that f at x naught plus delta x can be equated to, this is exactly equal to. So we are going to write the infinite series on the right hand side. So it's the value of the function at x naught plus the derivative of the function, the first derivative of the function evaluated at x is equal to x naught, multiplied by the correction, which I do not know. I do not know delta x, but the symbol is there. Okay, plus 1 by 2 factorial times the second derivative of the function evaluated at x naught multiplied by delta x squared, and so on. This is exactly what we wrote here in a different notation, right? So, but it is exactly the same. I'm using df by dx for f dash and d2f by dx squared for f double dash, etc. That's all. So this is a infinite series, therefore I'm putting this equal to. Now, what we are going to do is, we are going to say, well, I don't want these kinds of non-linearity showing up. Delta x squared is non-linear, right? It's a quadratic term. Then delta x cube. So all these things are coming. So I am trying to avoid non-linearity, but these non-linear terms show up. So what I would like to do is, I would like to stop or truncate after the first order term on the right hand side. So I'm going to stop at this term, and I'm going to call the rest as higher order terms. So this familiar expression. So I'm going to ignore the higher order terms, right? Because I'm saying higher order terms are going to be small. They're not going to contribute as much to f of x naught plus delta x. That's my hope. That's a wrong hope, but that's something that makes the problem easier. So the value of the function at x, which is the new value of x, right? So the value of the function at the new value of x is equal to f at x naught plus delta x, the original x value, the previous x value, corrected by delta x, right? So I can write it like this. In using the Taylor series expansion up to the linear term, I can write it like this. Now I'm going to pretend it's not true, it's not necessarily true. I'm going to pretend that I've reached the root. That means f of x is going to be 0. That's my hope, and that's what I'm going to pretend. So I'm going to just say, well, with this correction, I've done such a beautiful and accurate correction that my function is going to be 0 at this new value of x. So I'm going to set this f of x to 0. So this is just fond hope. But nevertheless, we will get 0 is equal to, the right hand side is going to be f of x naught plus f dash of x naught times delta x. Now, if you rearrange this equation, I can get delta x, which is the correction, to be equal to minus f of x naught, because this goes to this side, divided by f dash at x naught. So this is the correction to my current guess, the expression for that. It is the value of the function at my current guess divided by the derivative of the function at my current guess multiplied by a negative sign. That is going to give me delta x. And so I can write the new value of x is going to be the old value of x, which is the symbol x naught, minus the function evaluated at x naught divided by the derivative of the function evaluated at x naught. Please note, including this minus sign is nothing but plus delta x. So in other words, x new is equal to x old minus f at x old divided by f dash at x old. So all you do is start with a value of x old, let's say 1. Then compute the value of the function, because the function is given to you. Find the value of the function at your current guess value. Take the derivative of the function and evaluate it at the current guess value. Then calculate x new. Check if the function at x new becomes 0. If it becomes 0, then you say, well, x new is the root. If the function at x new is not equal to 0, is not within your tolerance, convergence tolerance, then you set x old is equal to x new and repeat this again, right? So iterate. That's the broad idea. So the idea is this: start with a value of x which is equal to x naught, or you can call it x old. So this is your starting guess value. So you need a starting point. Then what you do is you find the value of the function at x old. This is your current guess value. If the function value is 0 or it is less than your tolerance, like 10 power minus 8 or 10 power minus 12, then you can say stop. Okay, because in a machine, in computers, you cannot get exactly 0, right? You will get a number that is smaller than the machine tolerance, or something that you find is okay. So 10 to the power of minus 8 or 10 to the power of minus 12 is good. So this really is, it is less than or equal to 10 to the power of minus 8 or 10 to the power of minus 12 or 10 to the power of minus 15. So if the value of the function is a small value, right? Stop. Declare the result. You say the root is at x is equal to x old. Otherwise, what you do is you create a new x, which is equal to x old minus f at x old divided by f dash at x old. So this is the Newton's correction. This is the smart correction, assuming a linear kind of function. So that is the assumption behind this. You believe that the system is linear in its behavior around x naught. It may not be the case. That is why you have to iterate multiple times. Otherwise, in one shot, you will get the answer. And then what you do is, once you calculate this new value of x, you have to say x old is equal to x new, and then go back here, because this is always based on x old. So once you calculate the new value, what you do is you set x old is equal to x new. So the new value is assigned the symbol x old, and then you go here again. Find the value of the function at x old. If it is smaller than your tolerance, declare this to be the answer and stop. If not, find out an improved guess, right? Find out a new x new. So you will start at x naught, then you will find out f of x naught. If this is not within the tolerance, right? If this is not within the tolerance, then you will calculate x1, which is equal to x naught minus f of x naught divided by f dash of x naught. Now you now calculate the value of the function at x1. If it is small, if it is less than tolerance, declare the answer. If it is not, then calculate x2 is equal to x1 minus f of x1 divided by f dash of x1, right? And again, keep repeating this procedure. So I hope you understand how this iteration works. So you iterate until your tolerance is reached or until you get frustrated, which means you can say, I'm going to allow a maximum of 100 iterations. So starting from a reasonable initial guess, I hope the iterations will converge in about 100 iterations. If you take more than 100 iterations, you might say, well, I will stop the algorithm or I'll let the algorithm stop by itself, and you will work with a different initial guess, right? Because the initial guess may be poor. So this is what is called the Newton algorithm for one variable system in one unknown. And this algorithm, Newton's algorithm, is great. It works well if the initial guess x naught is good. If the initial guess x naught is bad, it might not converge. Okay, so the Newton algorithm is great. It has some beautiful properties like quadratic convergence. That means very fast convergence, but it is based on the assumption that we have a very good initial guess. All right, and industry folks often have good initial guesses. All right, because they have engineering knowledge, so they usually start with good initial guesses. So let's stop here and catch up in another video. Thank you.